All right, so we're gonna wrap up 13.4 today. I'll have the homework assignment for you. It's at the end of this section. I'll show you those, and we're gonna start 13.5 today. Hopefully get through most of 13.5. If there's a chance, we might start 13.6. 13.5 is pretty short. Okay, but we need to finish up 13.4, which was Green's theorem, right? So let's say that I have some interest in figuring out the double integral over this region D, but this is not a simply connected region. Remember, I said if you take out the center of it, then that's not anything we dealt with. You can't shrink it down, can't shrink a curve down through that hollow part, that hole. All right, but we're going to investigate this, and we're going to get a pretty amazing result when I'm done with this, all right? And then we're going to be able to answer a pretty, like what appears to be a very difficult question. We're going to be able to do it with pretty good ease, I guess. All right, so see the region? I'm going to take that region right now, and I'm going to come in and I'm going to cut it. So I'm going to cut it here and just here. And that's going to create two regions, which I will call D1 and D2. All right? I am also going to define two paths on this object here. The first path is going to go in this direction, counterclockwise, which is positive orientation or negative? Positive orientation is counterclockwise. I'm going to call that path C1, okay? I'm going to define another path. I'm going to have to use red because I'm running out of colors here. Another path which is going to go around the smaller inside part, and I'm going to orient that clockwise. All right? Got it? And I'm going to call this C2. So I have a big region D, which I'm going to cut into two pieces, and I'm looking at two curves on that region, one that goes around the outside and one that goes around the inside. One of them is positively oriented, the other one is negatively oriented, right? Now imagine that I actually physically come in here where I cut that and pull these two apart to put some space between them just so we can look at them, all right? Now, I'm not going to be able to do an exact copy, but I'll do my best. All right, the top region goes something like this. I cut it here, and then it goes like this, like that, and then the bottom one, something like this, comes over here, drops down, right, goes like that. Yes? You agree? All right, now I'm going to put some points on here. Here, 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 here. And I'm now going to label some paths on this, all right? Not those paths, not C1 and C2. I'm going to call these different things, all right? I'm going to look at the path that goes this direction, like this. Comes all the way back around, right? That's a nice closed curve, isn't it? Let's call this first piece right here, just this path that goes from this point to this point, let's call that E1. Let's call the path that goes all the way around like this to that point, let's call that E2. The path that goes from here to here, let's call that E3. And the path that goes in this little kind of circular shape here, E4. You with me? The region inside, remember, this piece in here is D1, isn't it? That's D1 inside. Now I'm going to label another set of paths on this one. And it's also going to be the same, actually opposite orientation. Hold on a second. Yeah, let's go opposite. So like this. Sorry, I'm saying opposite. Just ignore what I'm saying. I'm saying the opposite of what's happening here. So let's do it positively oriented like this. Okay? With me? I'm going to call this little piece from here to here, call it F1. Call this F2. call this F3, all the way back around F4. Okay? We all right with this? All right. What I'm interested in is the double integral. I'm going to use Green's theorem here. The double integral over d, partial q with respect to x minus partial p with respect to y. That look familiar? Yes? That should be equal to the double integral over d1 of the partial q with respect to x minus partial p with respect to y dA what? Plus double integral over d2 partial q with respect to x minus partial p with respect to y dA. We agree with that? That's just the fact that when you do a double integral over a region D, that if those regions are connected together, you can do them separately, right? So that's fair. But by Green's theorem, this integral right here, just this one, this double integral, should be equal to the line integral, right? Green's theorem, the line integral along the curve that encloses D, as long as that curve is in the positive orientation. So notice that this is positively oriented, right? So this right here, just this, should be equal to the line integral over this whole path. But since I broke it up into smaller paths, do you agree I could say line integral over E1 of, what is the formula? P dx plus Q dy. All right? Then plus, hold on a second. Yeah, E2. So I'm moving here to here. Now go around here. That's E2. So plus integral E2 P dx plus Q dy plus what? E3, E4, right? To save room, I'm just going to put integral E3 blah plus integral E4 blah, right? Same thing I had over here. All right, that's this one. Plus this one, which should be, now I'm moving around D2. Here's D2. It's positively oriented, right? So I move around that one. And when I move around that one, I'm going to have line integral over what? Let's start at F1, okay? F1 of the same thing, right? P dx plus Q dy. So blah plus what? F2 blah plus F3 blah plus F4 blah. Yes? Everyone agree with this? All right, anyone see anything interesting in here? I'll give you a hint. Do these cancel? Do these cancel? They're opposite directions. Do you notice that E1 is the opposite direction of F1? In line integrals, if you change the direction, you get the same answer but negative. So this integral right here over this path should cancel out with the one over F1. And E3 should cancel out with what? F3. And what's left is pretty amazing, I think, if you see it. What is E2 and E4, right? That's what we have. F2 and F4. So let me do it this way. I have to erase here. Remember, that's what we're looking to get, right? That's what we wanted to see what it turned into. This should be, I want you to look at E2 and F4. What's E2 and F4, those two paths put together? Which is C1. That's the outer one, right? That's C1. So this is just the line integral over C1 of P dx plus Q dy, right? Plus, now, what's the others that are left? What's E4 and F2? Where is it? C2, right? It's this right here. E4 continuing on to F2 gives me C2. Understand? P dx plus Q dy. That's it. Okay, now that may not seem like a big deal, but it's going to help us out here quite a bit in just a second. What it's saying, what this whole derivation is saying, is that if somebody gives you a region, right, and you have this curve that goes around it, and you punch a hole out of the middle of it, and you have another curve that's oriented opposite, right, that the relationship between the double integral over this region and the line integrals enclosing the two little loops here is this. Okay? That's pretty cool. All right, now let's move to the example. Now I put that in my notes, okay? In the notes that you print offline, but I did it a little different in my notes online, and it's harder to follow, I think, than what I just put up here. I hope. If you've looked at my notes, I don't go in as much detail with the notes. I don't break it up as E1, E2, E3, E4, F1, F2, F3, F4. So it's harder to see that cancellation happening. I just kind of say, hey, look, these cancel, they're opposite directions. So just remember this, all right? Now, how can we use that result? So look at this question. Show that the line integral of the vector field f dot dr, which could represent work, right? This could represent work. It's not necessarily in this problem, but what is the line integral of the vector field f dot dr over the curve C, right? Show that that is equal to 2 pi for this vector field where C is any closed path enclosing the origin. So that's saying if I take the xy plane, here's the origin. If I draw any path, right? Any path. Ooh, I need to throw that away. Okay, heads up. All right.
Better be good.
Oh, that was total luck. See, I kind of stretched out first. All right, so if I take any path, any closed path that encloses the origin, that if I do the line integral over that path, it's going to be 2 pi. But the key word in the problem is that you're supposed to show this happens for any curve. So how can you possibly ever do that, right? I mean, you can't check all the curves that enclose the origin, can you? You can't. I'm about to use what we just derived a second ago, all right? And here's the way I'm going to do it. First of all, let's just call this path C, all right? And I'm going to have positive orientation on this path. Let's call this C. I'm not going to call it C1, all right? I'm just going to call it C. That's this path. That is an arbitrary path, right? Then I'm going to come in here and very cleverly, if that's a word, I'm going to choose a positive number, A, such that the circle with radius A is inside C. Do you think I can do that? If somebody draws a curve, right, any curve, where the origin is inside of it, but not on the edge of it, right? Can I choose a small enough circle so that I will be inside that curve? Yes? Because, yes, the answer is yes. And the reason is because if this curve does not touch the origin, then there's some gap between the origin and the curve, right? And I can always choose my A to be half that distance. And I'm never going to run out of positive numbers that are greater than 0, right? So I can always fit this little, later on if you actually study math, we call these little epsilon balls. If you can fit a little epsilon ball inside of here, then I can do it, right? Yes? No one's going to argue with me on that?
What if it's on the curve, or like the curve goes through the origin?
Okay, so that's why it says it encloses the origin, and what we mean by that is that it is not on the curve itself. It doesn't say it explicitly, but just so we understand, that's what they mean. All right? If it lives on the curve, that's a different story. The origin is on the curve. Okay, so let me draw this little circle that I'm going to put in here. And just so you can see it, the A might be smaller, but that circle's right here. It has a radius of A. You with me? I'm going to orient that the same direction. I know in the previous thing where I was deriving the formula, it was the opposite direction, but I'm going to do this in the same direction like that. And I'm going to call this C, you want C1 or C2 or C sub A? What do you want? C1? I heard C sub 1 first. Is that okay? So we have C is the big one, right? That we started the problem with. It's an arbitrary curve. And I'm coming in here and I'm constructing a smaller circle inside that curve. With me? Okay. What can I do next? Let's talk about what the line integral over C of f dot dr plus, let's just look at what this is, plus negative C1 of f dot dr would be. I do realize I put a negative here. That means I'm going to reverse the direction. Okay? Well, this, by the definition of this is C P dx plus Q dy plus this C1 of P dx plus Q dy. Do you agree with that? If you did the bonus problem, you know, I think, that this is equal to this. Okay? That this is equal to this. And can you tell me what that is? So look, what does negative C1 look like? It's the same curve, but the opposite direction. Do you agree with that? So everyone agrees it's that in the opposite direction. Isn't that what I just had on the board a second ago? Didn't I do that? If you had this region D, I cut out a circle. I said this way on this one on that one, right? And we said that this really makes this equation true. It says this was C1, this was C2. Said line integral over C1 of blah plus line integral of C2 blah would be equal to double integral over D, right, of the partial stuff. Well, this C goes positively oriented. This negative C is negatively oriented, just like in the formula here. So shouldn't this turn into Green's theorem? Yes? Okay, so keeping that equals going, okay, keeping the equals going here, this should be equal to the double integral over what? The entire thing, right? The entire thing, that's D. right? Or is it without the circle? Hold on. I did too much. What was D in the last one? This right here. D was the region between them, sorry. Yeah, so not including this, right? You all okay with that? Of what? Partial Q with respect to X minus partial P with respect to Y D A. Yes? We're all good? Okay, now, still, I mean, I don't think it's obvious from what I've done why I've done it, right? It's just watch what's going to happen. Why would I have looked at this to begin with? It's only because I realized that I derived that formula before and I need these paths to be in opposite directions and I want to try and get to Green's theorem. But this may turn out to be a disaster. So I'm going to leave this right here on the board. This equals that. Can we do some partials real quick? What is the partial of Q with respect to X? What is partial of Q with respect to X? You have to do a quotient rule, don't you? So I'm going to do that right here. Partial of Q with respect to X is equal to derivative of the top times the bottom minus the derivative of the bottom. Two x times the top all over x squared plus y squared. Are y'all all right with this? Seems like I lost y'all there. Right, this, oh yeah, squared. Okay, what does this thing turn out to be up here? You have x squared plus y squared minus 2x squared is what, y squared minus x squared? You agree? Okay, that's what this is. Minus, what's the partial of p with respect to x, with respect to y? Partial of p with respect to y. I'll do that here. So derivative of the top, -1 times the bottom, x squared plus y squared, minus derivative of the bottom with respect to y, 2y times the top, -y over the bottom squared. And what does that top one turn into? Y squared minus x squared again. So these are the same. And I'm subtracting them. I'm supposed to take this one, subtract this one. So this is what? 0. And the double integral of 0 is 0. Okay. Now this is pretty awesome because this means that this plus this is 0, right? Holy shit. That means that this plus this is 0, which means that these are the same. I mean, sorry, they're opposite in sign. Sorry. You can just move this one over, right? So I'll do it. The line integral over C of f dot dr is equal to the negative of this, right? Yes? But taking the negative of this is the same as reversing the direction. Yes? So why don't I erase that negative and make that that? Yeah? So what is this telling me? If I want to know this line integral over some arbitrary c, which I never told you what it was, it's the same as the 1 over c1. But that was just a little circle. Now, it only works for this particular vector field. This is not a general conclusion that we're drawing. It's for this particular vector field we're able to do this. And so I think we might be able to do that pretty easily. Let's see if we can, right? Let's see if we can actually do this one. Yes? Why is it only working with this one? Because that's 0. If those partials had not turned out to kill each other off, this wouldn't help us at all. Which is why when they tell you in a problem like this to show this is true, most likely when you go to Green's theorem, you're going to get zeros, or you're going to get 0 to come out. Okay, so I am trying to find, right, this whole problem of trying to show you that this line integral over an arbitrary curve is equal to 2 pi has reduced down to me showing you that over an arbitrary circle of radius a, the answer is 2 pi. So I just need to know this. What is the line integral over C1 of f dot dr? So how would you like to do this? You have options. You want to define C1 as a curve? So let's draw C1. To draw C1, I use a vector function, right? What? What's the radius of that circle? A. So A cosine t, A sine t. That should draw me the curve. T, of course, is bounded between 0 and 2 pi. So that'll draw me that circle, radius A. Now, I think what you're doing, from what I'm hearing, is that you're going to go in here and go 0 to 2 pi. You're going to take the vector field, you're going to plug in r of t, and then you're going to dot that with the derivative of r of t, or of r, and then dt. I believe that's the formula that you're using here. Okay. So we need the derivative. The derivative of r is what? Negative a sine t, a cosine t. You with me? And we get to plug that in, right? We get to plug the r into the vector field, and we need to plug the r prime into this. So here I go. It doesn't look nice, does it? Doesn't look nice, but it's going to clean up pretty good. Equals integral from 0 to 2 pi. And then the vector field with negative y. What's negative y? Negative a sine t. Over, what's x squared plus y squared? If you take these two, square them, and add them together, you'll get a squared after you use Pythagorean identity. So you're just going to get that over a squared. And then there's no square root, right? We're good? Oh, yeah, OK, you canceled already. Yes, I'll do that in a second. Now the x over x. So a cosine t over a squared again. And then I'm going to dot that. Vectors. My angle bracket there is wanting to be something else. OK, and I dot that with the derivative, which is negative a sine t, and then a cosine t, and then dt. And I think we're going to get a really nice result here. When I do this one and this one together, negative a times negative a is a squared sine squared t over a squared, which is just sine squared t. And this is a dot product now, right? So I'm no longer going to have a vector. So I have sine squared t plus, and then same thing happens here, right? A squared cosine squared t over a squared again, doing this one times this one. And the a squareds cancel. You're just with cosine squared t dt. But that's just integral 0 to 2 pi of 1 dt, which is t evaluated 0 to 2 pi, which is 2 pi. So this is a really good example of how something like Green's theorem, although it's nice and we've seen it's useful, if you use it the right way, you can take a problem that seems impossible to do and do it, right? Now, a lot of times in classes that you would take like physics or down the road, a lot of times these results are known. So like for particular vector fields, you know that if you go along any closed like loop, you know that the answer is going to be 2 pi. And they more or less provide that to you rather than derive it for you. And so in this class, what we're doing is we're trying to derive where it comes from. Yeah? Okay. All right, moving on. That's the homework. There is not going to be a homework problem like this. I'm not going to give you a test problem like this. This is just to show you kind of the power of what we can do with the Green's theorem. I think that's like the first time I've ever run through that without making any mistakes. There's a lot in that to have to regurgitate. Got that? Okay. The next section is pretty short, it's pretty clean, and it's very visual, all right? I try and make it visual because I think these are two of the coolest things that we can see in this class. It's this idea of curl and divergence. So we know that we have these things called vector fields, right? And if you look at a two-dimensional vector field, that basically says like a flat sheet of paper, at every point there's a vector that points in some direction. And in three-dimensional space, the same thing. So before I talk about these two things called curl and divergence, I wanted to just mention, just look at something visually. I was going to try and give you, bring in an example to show you, hands-on thing. But let's just imagine that we're looking from the top down, and we have this pivot point, and we have this piece of wood, all right, like this, all right? And let's not look at like gravity is down or anything. Let's just say there's no gravity. In fact, we're looking at it from the top, so gravity wouldn't matter. But if I push on this with a force here and a force here at the same distance from the pivot point, and I push with the same amount of force, what's going to happen? No, this is a pivot point, and it's locked in place. Okay, that doesn't move. Well, let me do this. What happens if I just do that? Start spinning, right? It would start spinning this way, yes? Or if we want to look at this almost like a paddle wheel, and you turn on a fan over here and you start blowing, and this will start spinning, won't it? But if I put a fan over here and start pushing with the same amount of force that direction, it's going to be stuck, right? It's not going to move. Okay, and if I do something like this, where I push with a lot of force right there, but then I put, a little bit of force over here, that still might balance